Okay, hey everyone. So today I am going to be presenting this paper, Inductive Representation Learning on Large Graphs. It's an older paper. It's not a new paper. It's from 2018. But I wanted to present it because I think it's actually quite a approachable paper. And it also has, like, within NPlan, we use some of these methods for being able to run like machine learning on graphs. And so I realized that I had a gap in my knowledge about this. So I kind of wanted to read and get up to date on it. So the paper is called Inductive Representation Learning on Large Graphs, but what they build and what came out of it is more commonly known as GraphSAGE. And SAGE stands for sampling and aggregating. And I'll get more into like why that is. But the inside, or the sort of reason behind the paper, is that at the time in 2018, back then, most approaches of like learning embeddings in graphs to be able to do like downstream applications like node classification or link classification or these kind of things were transductive, in the sense that what you typically do is you'd have a graph and you would learn representations of the nodes and links in that graph based on that static graph. But the problem with that, as you might already be seeing, is that it doesn't generalize to like new subgraphs or evolving graphs or just completely like unseen nodes. And what that means is these methods, these transductive methods, are inherently limited in their usefulness and the use cases. And so what they do in this paper is they think about, like, rather than learning representations for individual nodes in one static graph, why don't we use this graph to learn sampling and aggregating functions, that then can generalize to new graphs, or perhaps the same graph like evolving with new nodes. And this would be like the inductive method. So effectively, rather than learning specific representations of nodes within the graph in the training data, we're learning functions, and those functions can be applied on unseen nodes or new graphs to create representations and embeddings for those nodes that can then be used in downstream tasks. And so this can be super useful, right? So imagine they have a few different like data sets that they evaluate this approach on. They have like a citation data set, Reddit posts, and a data set of protein-protein interactions, where they have like the data set is composed of multiple separate graphs. And these it's useful. This method's useful because these graphs, like take Reddit for example, is like ever evolving, right? You have new posts all the time. You have new users all the time, and so how can we build functions that sort of generalize across the whole Reddit graph, rather than having to run like training or create new embeddings at each time step. So the background is obviously like, why do we want to do this in the first place? Is that like having embeddings of nodes in graphs is like, and incorporating graph structure in those nodes, in those embeddings, sorry, is very useful for like graph prediction tasks. So you want to basically, in the node embedding, you want to capture information about that node, but you also want to encode information about its neighborhood and the graph structure. And that provides like much more powerful set of features when you're training models on specific graph tasks. But as I mentioned, yeah, the reality in life is that probably most graphs are like evolving. When we think about like social interactions, when we think about like Reddit posts or having new like proteins that we're investigating, or funnily enough, like the reason I came across this paper was because I saw that NatWest's AI team used this paper for fraud detection. So they have graphs of transactions across users, bank accounts, etc., different entities, and they use the embeddings created by GraphSAGE, this algorithm, to improve their fraud detection, which I thought was quite neat. And that's obviously like an ever-evolving graph with ever new entities. So as I mentioned, the sort of state of the art at the time was this kind of like transductive approach. And basically you would, let's say you have a graph, you would basically have some kind of algorithm. They compare a few here, which allows you to learn embeddings for each of the nodes by walking through the graph and using some kind of like gradient descent to basically like make nodes nearer to each other have more similar embeddings, and nodes further away from each other have different embeddings. And you can use that to then do like downstream classification or different types of tasks. But as soon as you have like new nodes or new graphs, you kind of have to go through this whole process again, because you just have no idea whether like the embeddings that are going to come out will be aligned with the previous embeddings that you had, which is kind of what I highlighted here. Like you need to make sure that the embeddings for the new nodes make sense in the context of like the previous embeddings that you have. But not only that, I think you need to you need to be able to like do this in a kind of like efficient way. You need to be able to like as graphs evolve, you want to be able to learn these embeddings like efficiently to be able to do, let's say, like online prediction on new kinds of nodes that come into the graph. And for that, you need to make sure sorry, there's two ways they sort of do that. Like one is by having like efficient sampling. So you're effectively not looking at the entire graph when you're creating the embeddings. You're sampling neighbors of like nodes to try to just capture some understanding of the structure of their neighborhood. And the second is instead of learning embeddings directly, let's learn functions to create embeddings. And those functions are, it's much more efficient to just like learn those functions, and then we can apply those functions to like unseen nodes. And this is what they call GraphSAGE. So at a high level, what GraphSAGE does is for each node, you're going to sample from its neighbors and then also sample from the neighbors of the neighbors. So you're kind of like going through like a few layers of depth, or I think they call this the search depth. And then what you do is, so this is the sampling step. This is the S in the SA in GraphSAGE. And then you take those nodes that you've sampled in the neighborhood and you apply an aggregator function. So you take the embeddings of all of those nodes and then you sort of mush them up and aggregate them, and then aggregate it with the current iteration of that node embedding to get the final node embedding for that one. And then you can use that in downstream tasks. So most applications will rely on having, each node will have some features which you can use as like the initial embedding. And then you can think of it as like these features get used, and those embeddings get refined to whatever like sort of output size and embedding size you need. But it's sort of like taking in information from its closest neighbors to adapt the embeddings. And doing so is like quite powerful because you in sampling from the neighbors and then learning from the embeddings, you're also just learning about the graph structure. And I'll show this later, but they actually have a really cool kind of demonstration of proving that it learns graph structure, where they basically have nodes which have no features. They randomly initialize the embeddings, and they show that the embeddings come out basically like learning some kind of graph structure. They can approximate the clustering coefficient, I believe. So you can sort of train these aggregator functions to capture things about the structure of the graph. And you can effectively train this approach in like two different ways. There's like an unsupervised way of training it, where they have like an unsupervised loss function, which we'll go over. And then, but if you have a specific task that you're looking to use the embeddings for, you can also train GraphSAGE in that kind of supervised manner, and it does lead to some improvements in the final task. Although the improvements weren't like as drastic as I thought they would be. I thought training on the final task would lead to a significant uplift, but it's actually not so much. So yeah, as I mentioned, they evaluate on 3 different benchmarks. So they have the citation data and the Reddit post data. Both of those are like classification tasks where they're trying to predict the categories of the papers in the post. And the last one is a multi-graph data set of protein-protein interactions, which is predicting protein functions. I must admit, all the protein stuff like went way over my head, but I think the kind of interesting thing here is that this data set is not one graph that's evolving. This is basically, you have like, in your training data, you might have 10 different graphs, and then the job is to predict on completely unseen new graphs. And so they evaluate on this kind of task as well, which is a bit different to the other ones. And yeah, they show that it, like GraphSAGE, can consistently outperform some of the previous transductive baselines. I'm gonna kind of skim over this, but it talks a little bit about the background of like different kind of methods that have been used in the past, which are the transductive ones. And as I mentioned, you directly train on node embeddings for individual nodes in a static graph. And the way these have been sort of tailored, or were being tailored to unseen nodes, is that you would sort of continue training, or you do some kind of retraining. So you have to keep you have to do more rounds of gradient descent, basically, once you have new nodes, to then be able to include those nodes and do prediction on them. And so this is kind of, this is quite expensive to do if you think about doing it on like every new prediction where there's a new node. They also compare their work to graph convolutional networks. And I think they've taken effectively like a sort of inspiration, I think, from graph convolutional networks, where they do like they learn, I guess, the functions that are applied over the neighborhood of specific nodes. Okay, so going into a little bit more detail of the algorithm itself. So how does the forward propagation work? So how does the prediction work? So they have a good description here. So you have a graph with some vertices and edges. Each node has a set of input features. You have a hyperparameter k, which is basically your like I believe it's your search depth, although I think confusingly they use K for, okay, so sorry, you have a different aggregator function for the search depth, basically. So this is kind of a hyperparameter, right? So the higher K is means the more like layers, if you will, of the graph you're going to explore, the more hops you're going to take across the graph. But obviously, it's more expensive, it's more parameters. So it'll take longer, and they do some studies to understand what a good value of K is. But yeah, you have different aggregate functions that aggregate over all of these hops over the graph. Yeah.
In principle, this could also be just one function that is applied several times in order to get the multi-K hops, right?
Yeah. Yeah, I think so.
Because I don't think you necessarily have to have an explosion in parameter space for this to be.
True.
Yeah. Okay.
That's very true.
Cheers.
Right. So so the way the forward propagation works is you initialize these embeddings with the node features for all nodes, right? And then you go through like the initial neighbors, and then you basically aggregate. You apply the aggregate function based on the neighbors of V in this case, which creates this like one vector, which is the aggregate of all of the neighbors, and then you concatenate it with the previous sort of the previous like iteration of the node embedding, and then you apply like a nonlinearity, and you have some weights as well, and then it gets normalized. So effectively, you like go, let's say K is 2, you do like 2 hops where you aggregate nodes, the second level neighbors, and then you aggregate again, and in each step you have like some weight and nonlinearity applied to it, and then the weights it gets normalized at each iteration as well. So yeah, as it says, as this process iterates, you gain more and more information from further reaches of the graph. So effectively, like first you aggregate information from your direct neighbors, then you aggregate information from their neighbors, etc. Yeah, so the nodes are selected using just a sampling. I think it's just uniform sampling. I feel like they mentioned that somewhere. But yeah, that's also a hyperparameter, I believe, in the algorithm. So it's not done for all neighbors. I feel like it was here somewhere. Yeah, I can't remember. Yeah, good.
I think in principle you can just almost treat it as a batching problem, right? That all it says is you can effectively batch without having to look at the whole graph, and so you can in principle think of one epoch as one iteration over your full graph. If you have say one mega large graph as your training set, and because it's batched, you can iterate over it several times, right?
Yeah. Yeah, so interestingly, they kind of related to a different like test for isomorphism. I didn't come across this test before, but effectively, if you if you think of the aggregations as a hash function, and you kind of do the same where you're going through from a node, like through all the nodes in the graph, and you're applying this hash function, then it creates some kind of test for isomorphism in the final set of representations of the nodes. If they're identical, then the graphs can be considered to be isomorphic, which I guess is interesting in the sense that maybe what they're trying to suggest here is that that the inspiration for this was to learn the structure of the graph, not just look at the node features independently. Yeah.
I think what this comes down to is that, graphs are incredibly arbitrary, right? Because the node name or the order of the nodes is sort of random, right? So it's not a feature of the data set, but rather the edges that go between nodes. And I think the idea is that this Lehmann-Weisweiler test can see whether two graphs are the same bar from just renaming the nodes in some permutation. And since that is a sort of symmetry that you would like to have in your modeling, because it essentially means you use your space efficiently, right? Because if you had a model that predicts stuff based on how you label the nodes and which order you put them, and you get different answers, that would be an indication that something is not quite right. And by showing that these two methods are similar, it shows that at least on that level of similarity, similar graphs give the same answer if all it is the changes in the rows of your X matrix that make up your feature space.
Yeah, it's a really nice way of putting it, which sort of gives you confidence that it's learning the right things about the graph.
Yep.
Yeah. Yeah, thank you. So here's Jim, where the definition was. So we have the notation says neighborhood of V, but they kind of abuse that notation, because really it's basically just some uniformly sampled set of neighbors, and they draw different samples at each iteration. And they mention here that, so their approach works well with k equals 2, so you only go 2 hops, and also S is the number of samples at each stage, so the product of the first and second samples will be less than 500. I think they use something like 25 and 10 or 10. Yeah, I think something like that. But we'll look at the parameters that they investigate later. So how does so we've done the forward propagation. So we've basically done the message passing of the node features. How do we learn the parameters of GraphSAGE? So as I mentioned before, you can do this in an unsupervised way, or you can do this in a supervised way. The way you do it in an unsupervised way, which is similar to previous papers they suggest, is basically you encourage nodes that are nearby to have similar representations. And this is kind of similar to word to vec, which I saw being mentioned in the graph. So you kind of say, okay, like in word to vec, 2 words are co-occurring, so then they should have similar representations. You kind of do the same here with nodes. And yeah, they just mentioned here you can replace with a task-specific objective if you have. And then the cool thing is that you can learn sort of different aggregation functions, or here they call them aggregator architectures, because they have their own parameters as well that you learn. And they explore like ideally how these functions should be symmetric, because you should ideally, like, the same set of nodes in different order should provide the same output. But some of these aggregators are not symmetric, but still work well. So they explore three. They have the like simple sort of mean aggregation. You have the LSTM aggregation, and then a pooling, which is kind of like a one layer, like a single layer where you apply like the weights and bias and then the nonlinearity, and then you pool that output. So they compare these three later. So I'll go through like the difference in terms of like performance across all the different data sets. But the mean, I guess, is the most simple to sort of understand, where you effectively like average the embeddings of the neighbors, and then you like concatenate it with like the previous like representation of the node, and then you apply the weight and nonlinearity. I think what's kind of interesting that they mentioned here is that the concatenation of like the previous node representation with the new one, with the new averaged embedding, is kind of like a skip connection between the different search depths, and it leads to like quite improved gains in performance, which is quite interesting. And they actually compare like not doing the concatenation versus doing the concatenation. I thought this was quite like a nice, it helped me sort of think about why they'd want to concatenate with like the previous iteration of the representation. So yeah, the mean is like intuitively simple, but they also use like LSTMs as an aggregation to learn. And the reasoning behind it is that, you know, they can perhaps like be much more expressive than just like averaging embeddings, right? But they do note that there's not like symmetrics. They're not symmetrical. So what they do is they apply the LSTM to like a random permutation of the nodes, and I guess they do that to try to encourage to like sort of generalize better. And the last one's the pooling aggregator. So you pass like each node, each neighbor's representation is passed through a fully connected like single layer neural network, and then it's then all of these are like you apply either like a max operator, or you can also apply like a mean operator element wise, like on top of this. So you can decide how you want to pool them, but they find like that there's not much of a difference between max and mean, so they kind of use max in this case. But this is quite cool. So effectively, like the aggregator function we're learning here is like a simple single layer like neural network. Cool. So experiments. Let's see the results. So I've gone through the data sets. For the GraphSAGE, yeah, here's the values they use. So they use ReLU as the nonlinearity. They have k equals 2, and then the sample sizes are 25 and 10. So that means in the first iteration, they'll sample 25 neighbors. In the second iteration, they'll sample 10. So what they compare it to for the Reddit and citation data sets and what's considered the baseline is this algorithm called Deep Walk. Deep Walk, I had a quick look through the paper, but I'll admit I haven't gone through in much depth. But effectively, it does like random walks for across like the graph, starting from different nodes, and then it again has the same unsupervised like loss function where it tries to make sure nearer nodes have like similar representations, and nodes further away have like further away representations. But it does some kind of it does some kind of like, well, not aggregation, but it learns the nodes, the node embeddings directly rather than learning aggregator functions. So the way you like do online training, as it says there, is that you have to like run gradient descent again to create embeddings for the test nodes before being able to make predictions. This works for Reddit and the citation data sets, but it doesn't work for the protein interaction data set because it's multi-graph. And the reason is, like, let's say you have one graph and you learn embeddings for the nodes there, and you have like a new graph and you learn embeddings for the nodes there. I think those like embeddings are they have like rotational invariance, I think, effectively. So like the embeddings you learned here could just be totally like totally different and not aligned with the embeddings you learned for this second graph. And so if you train a model, a downstream model on these first embeddings, it will just could output just like garbage on the new graph. So they basically say like this kind of algorithm just can't work in this kind of setting where you have completely new graphs. So if we look at the results, so here's the 3 data sets. They train on a unsupervised loss and a supervised loss. Just as a reminder, the supervised losses for citation Reddit were like classifying the category of the post or the paper, and I forget what it was for the protein interactions. Classifying certain protein functions. Okay, classifying protein functions. If someone can illuminate what that means, let me know. But so we can see that like GraphSAGE across the board beats the baselines in some cases like quite significantly. So they compare a random model using just the raw node features, the deep walk with the features as well, and then the different GraphSAGE methods. But there's there's a significant jump, particularly in the Reddit data set, from deep walk to GraphSAGE. And generally, the LSTM and the pool aggregations work better than the mean and the GCN. Just as a reminder, the difference between the mean and GCN here is just that like concatenation of the aggregated neighbors embeddings with the previous iteration of the current node embedding. And that concatenation, that what they call that skip connection, results in this kind of improvement across the board. So they think that concatenation, that skip connection, is actually delivers like quite good results. And they compare also, another reason they wanted to implement this kind of method is that, deep walk and this kind of transductive method can work. You see like the performance is not awful in some cases, but you have to like train it on the test node. So you have to create the test node embeddings by running gradient descent for predictions. So you can see like the inference, this is like a log scale. So effectively the inference is like 100 times slower. Or is it 1,000 times slower? So yeah, it's like a massive improvement in terms of the speed of inference. And here this graph shows basically the experiments they ran with different sample sizes. So in this case, they had like k equals 2. So that you go 2 hops, and they had like, okay, let's sample the same for both iterations on the citation data. And you can see kind of like the performance sort of plateaus around this like 30, for this specific data set, around like 30 neighbors. But the runtime obviously like it sort of exponentially increases. So you need to find the trade-off that works for you, I guess. And I suppose this is quite dataset specific. You know, when thinking about the citation dataset, looking at like 30 neighbors per step or 25, like probably is quite, you know, gets you a lot of information already, which is why it sort of plateaus. But I wonder what it is for like other kinds of datasets. They explain a little bit here, like what kind of node features they used. So a lot of them were different, like sentence, like word or sentence embeddings. They used word to vec for the citation data, and then like glove vectors for the Reddit dataset. And they say they do some like processing of the features or feature engineering, where they concatenate like post title, comments, different things like that. And then here's the experimental sort of setup for the protein-protein interactions. So they have like 20 different graphs that they use for training. And then the F1 scores are based on like 2 test graphs, which are, as a reminder, like completely unseen, right? So these are 2 completely different graphs, but the aggregator functions are like effective on those kind of 2 unseen graphs. Yeah, and I guess the last thing is this. So they found that it was quite effective to use like k equals 2, which obviously provides like a big lift over k equals 1 in terms of the search depth. But they found that like increasing that gives like marginal returns. But again, I wonder how dataset specific that is versus like a generalized comment. I feel like, well, my instinct tells me it'll probably be depending on like the graph, what the graphs are like and the graph structure, but not sure. Yeah, so I think this is the last bit which I mentioned earlier, where you know, they do some kind of theoretical analysis to prove that GraphSAGE can effectively learn about graph structure, even though what we're pooling is, or what we're aggregating is like node features. We're not adding any graph like information to it. But the way they show that is that they prove this theorem, which is like basically showing that like you can find parameters for the aggregation functions such that you can approximate, in this case, like clustering coefficients to some kind of precision. And they have some like proof in the appendix, which I haven't looked through as much, but yeah, effectively, I think they basically just like, you can prove that if you just like randomly initialize the features for the nodes and you apply GraphSAGE, that you can learn this kind of like graph feature just through the process of like aggregating, like sampling and aggregating.
Did they actually give a loss function for that, or is it something they just say that there is a combination of parameters that gives you the correct answer?
They just prove that there is a set of parameters that can give you the correct answer.
But not how to get there.
Yeah.
How useful.
I think, yeah, they have some proof here, basically. Yes.
I will let you finish with that, Gerard.
Okay. I mean, that was it, really. I guess maybe just like as a quick recap, for me, the big takeaway of the paper is like it goes from it takes us from learning graph embeddings directly to learning functions that can generalize to new nodes, new graphs that of similar kind of entities, which means that when we come to doing like prediction tasks on the graph, we don't have to run an expensive training process to get embeddings, and B, like we get better performance even actually out of this. So presumably there's some kind of like generalization in the aggregator functions that is beneficial for like downstream tasks. Yeah, that's it. Yeah, Inika, happy to answer question.
Yeah, I was wondering about the offer smoothing thing, and then I saw Arvid put a comment on that. And in that mean aggregator part of the paper, it mentioned about skipping connection. Well, it was saying that with this aggregator, we cannot do skip connection. I was wondering whether skip connection will help with offer smoothing. They didn't mention it explicitly. I was just wondering.
No, I didn't mention explicitly.
If I imagine like skip connection, then you might want to like reach further nodes, but not like aggregates all the nodes that lead to that for like far away neighbors. No, I'm just wondering.
I think as long as the non-linearity that goes that it comes after the aggregation, right? So you typically have two steps: the aggregation and then the message passing from the node to itself, if you will.
Yeah.
And that one could be a skip connection as well, right? So that takes into account the neighboring information, but doesn't have to be overwritten by it.
So you mean like after here, you could have another skip connection?
Yeah, in principle, I think that could be a skip connection, right? So this W could by itself train itself in such a way that it essentially ignores anything that comes from the neighborhood and only passes for the HK-1.
Mm-hmm.
Yeah. And is it a way to not to over smooth? Like for example, in the case that neighboring nodes do not have similar features, can we solve that case by having the skip connection? I think that's the question that I was trying to understand myself.
I think yes, and I think so. What really is missing here is the edge information, right? Right now, I think that the moment you don't have anything about the edges, it sort of implies that either neighboring nodes are similar or they're dissimilar, but the model wouldn't have any way to figure out the difference because it can't tell the edges apart. I think I did a paper on football. They also use something like this football pitch, and there, for example, the edge node could tell whether you are on the same team or on a different team. And then once you have that information in there, then it could make sense for the model to figure out, hang on, similar nodes, similar edges, meaning we are on the same team. Maybe smoothing is actually the sensible thing versus saying that a opposing node, if say the opposing player is very good, I want to rather have the opposite effect on my internal representation. But in this SAGE variation, they can't really do that because there's no edge data in there.
Yeah, makes sense. Cool, thanks. There's a question on the comment on the chat.
Yeah. So question one is the paper's corresponding approach of adjusting the architecture of the network and training it still in favor for graph-related works, like the fraud detection I mentioned, or is the query-based foundational LLM plus schema plus graph dataset plus query approaches also as promising? Unfortunately, I'm not sure. I would love the answer to that. But yeah, I think like we at mPlan like still use GraphSAGE for certain graph tasks. And then I've seen it. Yeah, I guess I wanted to read about it because I saw it in that fraud detection case, but I'm not sure what the sort of state of the art is these days on graph classification tasks, for example.
There would be node classification, right? This particular problem that is being mentioned there. I almost can't think of a possible way of loading ever a complete graph of very large problems, right? If you have like a bank with I don't know how many millions of transactions every day, I don't think it becomes feasible to ever load the whole data set and apply anything to it, but rather take any k and then maybe take a very large graph that corresponds with a large k, and that will have to do as the answer. I think in practice it would also be quite annoying if your answer of whether someone commits fraud or not would depend on the full data set of everybody who ever had any transaction.
Mm-hmm. I think that's the thing, like, because we have, in that case, that setting, you have a lot of data to work with, probably, and then you can learn very like efficient representations.
Yeah.
Yeah. I also, curiously, because we use like torch geometric for GraphSAGE, so I kind of wanted to like flag it here as like a more practical ending in case you want to play around with it. And I was having fun basically seeing, okay, like all the hyperparameters they mentioned in the paper, like what do they apply to here? So for example, I think num layers is like the k that's referred to in the paper. So like your search depth. And if you wanna play around with different aggregator architectures, you have to go into you have to provide them as separate keyword arguments for this like SageComp, and they provide a few different aggregations. And I thought it was interesting that the default is mean, even though that's not the best performing one in the paper, but it is probably the more, like, it's more efficient to train, and might lead to less problems. So mean is the default, but if you want to play around with it, just so you know, you have to kind of pass in the extra keyword arguments. And you can change, for example, like the nonlinearity and the dimensions and things like that.
There's also, I think, a daughter library, is it fair to say, also for graphs, but with temporal graphs, but I think that's a lot less developed as this one.
What's it called, Arvid?
Is it? Oh God, I think it was also a graph geometric, but temporal graphs.
Okay.
I think it's also torch.
Okay.
But it's, yeah, I tried it a little bit. PyTorch geometric temporal.
Okay. Yeah.
Which is slightly more specific, right? Because temporal graphs have yet a bit more structure to it.
Oh, sorry. Yeah, I realize that.
It also interoperates, so that in principle you can use graph architectures from here and then essentially spin them out over time, which is quite.
Okay.
There's also, I have this book I put in the chat, which is, in my opinion, very good, and I might do a book review at some point about it. This geometric deep learning, which sort of knits together the ideas of the space in which data sits. Could be a graph, could be a 2D space for images, or a straight line for voice data, for example, and what model architectures are generic enough but yet don't explode in terms of parameter space in order to have this to avoid this curse of dimensionality. It's a very, very good book. Not always easy reading, but quite good.
Amazing. Yeah, maybe you can do a review at some point.
Yeah.
Great. If there's no other questions, then thanks everyone for joining today, and I'll see you in 2 weeks.
Thank you very much. Good talk.
Thanks, Gerard. Bye.
Thanks.